Hello, this is Eric, and today we'll be talking about some introduction to Bayesian time series analysis and time series models using a program called STAN. So the way that we've broken up the lecture is kind of into three parts. First, we'll talk kind of a very brief, high-level overview of what STAN is. Then we'll talk about some examples of kind of working with STAN output and fitting some simple models in STAN. And then lastly, we'll try to expand our knowledge of STAN to fit some basic time series analysis type models that we've talked about in class already. Things like DLMs and dynamic factor analysis and AR type models. So far, up to this point in the class, we're about 4 weeks in, and we started with some pretty simple ARMA type models, which are extensions of regression, but deal with a process or an observation model slightly differently. Then we learned a little bit about state space models, where we have a process model and then a data or an observation model on top of that. Mark's already talked about performing dynamic factor analysis, which is a dimension reduction tool for looking at identifying common patterns or synchrony in multivariate streams of data. We've also talked about dynamic linear models, which are similar to a regression model, but you can think about having a time-varying covariate or time-varying intercept. And then last, we've talked a little bit also about kind of these multivariate autoregressive state space models. So this is extending the state space model that we talked about early in the class in a univariate setting to this multivariate setting where we have multiple streams of data. We're potentially estimating multiple AR coefficients for each of those time series, as well as potentially their interactions or different observation or process variances, as well as any impact of covariates, either on the observation or the process model. So why would we want to do this in a Bayesian setting when we have tools like Mars? I think that Eli talked about this early on in the class, but the primary motivation is that Mars is very useful for fitting these types of models if your data are structured in the right way. So often, as often the case, people who work with time series that have very high resolution data, for example, in finance, have you can assume that a lot of those response variables are normally distributed. But in the case of a lot of the data that we have in ecology or fisheries, we're often working with count data or data that has a lot of zeros, missing observations. We might have skewed data so that it might have long tails or extremes in one way or the other. We might have non-stationarity with respect to the mean or the variance. And then finally, we might have weird constraints. So we might have survival rates that are constrained to be between 0 and 1, or diet composition data that's constrained to be within a simplex, for example, so that the proportions have to sum to 1. So all those kinds of data are problems that are typically not encountered by people who work in fields like finance. And so I think for this reason, we need to have a little bit more flexibility in the models that we're fitting. And so in this case, it makes it pretty easy to switch gears and perform all this estimation in a Bayesian setting. And we get very similar inference to what we would get if we were able to spend the time writing the code to perform the maximum likelihood estimation. So Bayesian models allow us to fit a series of kind of complex hierarchical models. These can be models that are nonlinear. They might have shared parameters across time series. So we could set this up to be hierarchical even, so that there are random effects, for example. And as I said before, this it's super powerful in that we can fit non-normal data fairly easily. It changes our inference a little bit, and so I think that a lot of the quantities or the quantities of interest that we're going to be generating or the outputs are useful because that they are probability distributions. And so if we're trying to communicate results to managers, it's easy to present output and say the probability of a fish stock dropping below some threshold, for example, 40% of BMSY, or what's the probability of a stock collapse, or what's the probability the stock experiences an extreme negative or positive anomaly or extreme positive recruitment event. Those are all quantities that we can address. The other thing that's great about the Bayesian model is that in generating parameter estimates or confidence intervals for some of the models in the Mars framework, we have to do this kind of two-stage approach where first we fit the model with either the EM algorithm or strict optimization using BFGS. And then second, we take that best model and we do this bootstrapping procedure where we generate a bunch of new data sets and have to refit the model a large number of times. And often that involves 200 or more iterations. And so if each of those takes a few minutes, quickly time adds up, and then the next thing you know, you're running a computer overnight. So in a Bayesian setting, what's great is that every individual model might take a little bit longer to fit, but we don't have to do this bootstrapping procedure because we get our posterior credible intervals for both the parameters and the estimated latent states of the model at the same time. And so why are we going to use Stan for this class? We had started adopting Stan a couple years ago, I think 2 iterations ago. And we've started to really have it be the focus of a lot of these Bayesian models because it's a powerful, very powerful cross-platform tool. We can call it from a lot of different languages, and so for this class we're primarily using R. But if you're a MATLAB user or you want to use Julia or some of these other tools, all of them interface very nicely with the same underlying Stan model. So that's super flexible. There's a great team of developers behind Stan, and the example or the manual of examples is just growing. It seems like on a monthly basis it's growing exponentially. So they're adding a bunch of new features. The Stan community is great and very responsive at addressing questions and issues that come up. What's kind of cool about this is that we will do most of our estimation in a Bayesian setting, but what's great is that the Stan model can also be optimized using maximum likelihood very easily with a very simple call. So we can compare the results from this type of model to, say, a Mars model very easily. Some quick links that are useful for this class just as resources. The Stan homepage is here, as well as a link to the Stan manual. And then finally we have the RStan package, which is what you need to install Stan for this class. So that's on CRAN. The options for using Stan in this class, in an ideal setting, if you're thinking about your class projects and you're interested in using Bayesian models, it would be awesome if you were interested in putting together a simple script to actually do the estimation with help from any of us. I think that would be really useful and a good learning experience. You can also use an existing package. There's a number of different R packages that have already bundled a lot of these Stan models that could be useful. And then for the purposes of this class, we've already started, a couple years ago, we started bundling some of the basic time series models that we're talking about that are very similar to what we've been doing with Mars to kind of get you started. And so I think these could be a useful tool, either using these directly or just taking our code and extending it to your application would be pretty useful. So those are 3 different options. There's primarily 2 different packages already on CRAN that let you fit a lot of the basic time series models. So the 2 packages are RStanArm and BRMS, and both packages allow you to fit a really wide suite of models that include both fixed and random effects. The syntax for these is, it should be very familiar to anybody who uses R. Because it is the exact same formula syntax, and so there's in the RStan RStanArm package, for example, there's a simple Stan version of a linear model object, a Stan version of a GLM, a Stan version of a linear mixed effects model with different response structures. So this could be a logit model, a binomial family with a logit link, or a Poisson family with a log link, and so all these packages let you fit. If you have kind of hierarchical model with not a lot of complicated autocorrelation, these kinds of functions are probably a great first step. BRMS even goes a couple steps further and lets you include things like some autocorrelated errors. And again, like the functions we saw in the last slide, we have some non-normal data, nonlinear smooth terms, etc. But I think what's one potential limitation is that it doesn't include multivariate data, and it doesn't let us put any of these AR processes on parameters or any of these latent variables. And so I'm thinking about like a DLM or a DFA where we have this latent trend or a latent process on a coefficient. Those are models that we can't really fit using BRMS. So those are really only a couple of limitations. Otherwise, it's a great package. It's widely used, really easy to use, and again, the developers are really great at responding to any issues that come up. So again, like with the rStan-arm package, the BRMS package syntax should be very familiar, where we have kind of a fixed and random effects using our standard R formula syntax with any interactions or covariates easily put in. We can have grouping variables where we're denoting random effects. We can have very flexible families of different responses beyond just a Gaussian distribution. And then one thing that's cool that BRMS adds is that for anybody who's used a GAM and is familiar with fitting smooth terms, there's similar approaches using a Bayesian, essentially fitting a Bayesian GAM using kind of this BF function to fit the smooth term here over this x variable. So I think that these things are again rapidly expanding. There's constantly new features being added. I think it'll be probably just a matter of time before some of the kinds of time series models that we're fitting in this class are incorporated. But for now, I think that just be aware of kind of the strengths and limitations. Okay, so to run the code for this class using kind of the package that we put together, or the bundle, the first steps are going to be to install a couple packages. We need to install the rStan package, which will give us all of the code for actually running these Stan models or writing the Stan models yourself. And then we'll install the DevTools package if you haven't already, which will let us install some of the code or our bundled repo from GitHub. So those are kind of the first two lines. And then once we've installed DevTools, we can install this R package from our repository for this class. And this should be fairly straightforward and should run seamlessly. It includes scripts for about 15 or 20 different time series models, and so we'll kind of look at some examples of using these. Okay, so first what we'll do is just kind of look at fitting a super simple case that we've using a data set that we've run into before, and then looking at how we manipulate Stan output. So the time series here is just that same time series of river flow on the Nile River. These are annual measurements going back to the late 1800s. And around 1900 or a little bit before, there was this dam put in. So it's non-stationarity, and that we had kind of had this change point with respect to the mean, where we have kind of, you can see the level changed before and after that dam was put in with respect to the mean. Okay, so the first thing we'll do is we will fit a simple regression model to the data, which doesn't make a lot of sense because it doesn't include that change point in the mean, but it will kind of introduce us to how we fit the basic functions. And so next week we'll get into actually how to interface and what the Stan code is actually doing, and how to tweak it to change different parameters slightly, or how to write our own models. But for now, what we'll do is just kind of run the models that we put together for the class, and this will assume that we haven't actually done any Bayesian work before, and so this will be just kind of a first stab, and we've set it up to be similar to the kind of the standard syntax, in that we've got these helper functions that will basically take a few arguments and then let us specify the model type and fit the model without actually requiring us to get kind of deep into the weeds about what the stand model is actually doing. So this first function that we put together in our @sar library is just called fit stan, or fit underscore stan. And so the arguments here that it wants are going to be our response variable, the y, our covariates, which are going to be the x here, which is just going to be an intercept-only model where we're replicating this vector of ones for each observation in the data set. And then the model name here is just going to be one of a number of different models that we've already kind of hard-coded for you. And so in this case, we'll just be fitting a regression model. This is basically the simplest possible regression model. Okay, so then once we fit the model, you can inspect the object by looking at the output of this LM intercept object. And so you can see based on the last function call, we didn't actually specify any of the parameter arguments that you might be familiar with if you've done Bayesian modeling before. So typically you'll have to specify, for example, some kind of burn-in rate, basically the number of samples of the MCMC chain that you throw out before you start monitoring or saving parameters, assuming that things have converged from that point forward. We also haven't specified the number of MCMC chains, and ideally you would fit a model with a few MCMC chains so that you can theoretically start or initialize the model in different parts of the posterior surface, and everything will kind of converge to the same value. We also haven't specified any kind of thinning rate, and so in some cases, in some applications, people will thin MCMC chains to reduce autocorrelation. In other cases, they won't. That's probably less of a big deal as opposed to the burn-in or the number of chains. But we haven't specified that here because we've already built in some defaults for you. And so the defaults here were that the model ran for with 3 different chains. The warm-ups here, or the burn-in, was 500 iterations followed by 500 more iterations of sampling. And so if we throw out those first 500 and save the last 500 for 3 chains, we get 1,500 samples total. And then we can, so we have 1,500 samples to inspect with a few different helper functions. So given our samples, one of the first things we might want to do is look at what those samples look like, and so do some visual inspection of whether the posterior converged or whether the densities are kind of unimodal. And so there's a function in the rstan library called extract, and so the argument here that we pass in is one of these fitted model objects, and so once we pass that in, we can extract the parameters to either a data frame or a list. And so once we've done that, we can manipulate them and make some basic plots. So this is kind of the first case. So we have this object pars, which contains a few different variables. In this case, beta is just the value of that intercept that we were fitting. Remember, we were fitting a regression model with just a single parameter, controlling the mean, which is the intercept, and then we're also estimating a variance. So we can make a histogram of just kind of what that parameter looks like. Again, this is the log of river flow, and so it looks like things are okay. I think we clearly need more samples here, and probably need to run it for more iterations, longer burn-in, etc., just to assure that things are actually converging. But once we've got this pars object, we can also do any number of things that you would summarize any other kind of parameter, and that we can apply quantile or summary functions and generate medians or credible intervals, etc. So the class of that LM object or LM intercept object that we fit is the class is a stand fit object, which means it's a fitted stand model, And there's a lot of other plotting that we can do with that based on the rstand package. And so one of the first things that's really useful is using the trace plot function. And so in this case, the trace plot takes in a couple parameters. It takes in the fitted model object, which is that LM intercept, and then any parameters that we want to show. And so in this case, remember, we have two parameters that we're fitting. We're fitting this beta 1, which is the intercept, and we're fitting sigma, which is our observation variance. And what's cool is that, ideally, like I said before, we're starting the model for 3 different chains in 3 different starting spots, and we want to see that these chains are stationary with respect to both the mean and the variance. We want to see good mixing so that chains are not getting stuck at single values and not bouncing around. And so I think that these all actually look pretty okay, given that we've actually only run this for 1,000 iterations total with a burn-in of 500. And so we see that things are mixing okay. We also see all 3 chains are kind of converging on similar values. So without actually performing real diagnostics, things are looking okay. And with these trace plot functions are useful for fitting essentially all different kinds of stand models. Okay, second, we might want to also look at some of the correlations between parameters. And so this is particularly useful if we get models that seem to be not mixing very well, or there are certain parameters that might not be converging. I think it's pretty useful to use the scatter plot function. And so the way that we call this is in the rstand package, there's a stan underscore scat function. Again, we pass in our fitted LM intercept stan fit object. And then the different parameters that we want to look at a scatter plot of. And so in this case, we only had 2 parameters, so those are the only ones that I'm going to demonstrate here. But we have a, seemingly pretty low correlation between our intercept and our observation variance, kind of as expected. If we had a more complicated model with, for example, an intercept and maybe a slope parameter, we might expect to see a trade-off between the intercept and the slope. So there's extensions of this using more than just 2 parameters. But again, this is a useful tool, especially looking at diagnostics when things are not converging. I already showed you how to make a density or a histogram object kind of using the base graphics, but we can essentially do the same kinds of plots using the functions in the rstand package with the stan underscore dens function above or the stan underscore hist function below. And in this case, we're plotting some density and histogram plots for, again, that intercept and sigma. Again, and as I said before, you can see based on the histograms, things are looking okay, but not super smooth. So probably an indication that we would want to actually run this for quite a few more chains. Okay, so moving on, I think that there's a few other kind of plotting functions and helper functions out there to work with these stand fit objects. One of the most useful I found has been the Bayes plot library. And so when we install the Bayes plot library, one of the functions that's particularly useful is what's called an MCMC areas plot. And so in this case, we're just going to show the densities of densities of different parameters on the y-axis here, and then the values here. Unfortunately, the values here are not really on the same scale because our observation variance is quite a bit bigger than our intercept. But for any parameters that we're estimating that are on the same scale, this is a good way to visualize the densities, and then we can specify the probability threshold here, which is essentially designating where we want to shade the credible intervals. A similar way to kind of show the same information are just kind of this stand plot function, and so the stand plot is another way to show. I think these are called dot plots too, but again, we have the same information, not necessarily a density plot as was on the last on the Bayes plot or MCMC areas. example, but here we have essentially the same information in one-dimensional space. So we have, for each parameter, we have the shaded region represents the default. I think this is the interquartile width, so the 25 and 75% intervals, and then the line represents the credible intervals. We also talked about, one of the other good mixing properties of MCMC chains is ideally we would like to have parameters that have low autocorrelation, and we've talked about autocorrelation in the sense of, mostly in the sense of time series models and data for this class. But for these individual MCMC chains, we want parameters that are mixing well, and the lower the autocorrelation is, the more independent each of those different samples from the posterior is. And so I think in this case, we can visualize what that autocorrelation is using the stan_AC function. And again, I think for both of these, what these show is that even at lag 1, we have very low autocorrelation, which looks great. I think it would be much more problematic, for example, if maybe for our intercept, if our autocorrelation at lag 1 was 0.95 or 0.99, and then slowly trailed off from there. So I think both of these look great, and this is, again, just a useful diagnostic if you have poor mixing. So these plots are just kind of, really a few simple examples. There's a much wider and broader universe of plots out there. There's a bunch of examples on Stan that I think are really useful. Jonah Gabriel has put together a really good introduction to Bayes plot. There's a good vignette that this link will take you to. And then there's also a couple good examples that Matthew Kay's put together for Bayes plot and tidy Bayes. Again, these vignettes are super useful, and should give you a really good idea of how to present some pretty cool visualizations for these type of model outputs. Okay, so I think one of the things that we can get into next week, but a new addition to the Mars package has been some tidy, some incorporating some of the tidy functions so that we can get some tidy coefficient tibbles spit out. And so in this case, we can basically do the same thing with the Stan package, with the Stan models. And so in this case, we're going to use the Broom package, which has the kind of the tidy function. And so we can extract these summaries by passing in our fitted stanfit lm_intercept object, and then just look at what gets spit out here. And so in this case, this is a really fast way to get out kind of our basic parameter estimates as well as the standard errors of the estimates. In this case, what it's giving us is actually the intercept and the observation variance, that sigma parameter. But then also it's giving us the estimate and the standard error for each of our predictions. And remember, this is just a intercept-only model, and it's not going to include a change point with respect to that flow that we were putting in as the response. And so for that reason, because it's an intercept-only model, all of these predictions are going to be exactly the same at time step 1, 2, 3, 4, and have the same standard errors. So that's exactly what we see here. One of the cool features about these tidy summaries is that they can also be fed directly into a ggplot. And so in this case, if we just wanted to look at maybe we could make, or maybe we wanted to display the uncertainty around our predictions, we could just grab the predicted values in that coefficient object, which is kind of the tidy summary, and then plot the estimates with plus or minus 1 standard error. And so this is kind of what that looks like. This is not at all an exciting plot because, as I said before, this is an intercept-only object, which means that we don't have any time-varying parameters or coefficients, and so the mean or the level is just constant. So in this case, the value is or the error bars are going to be exactly the same for every value of the time series, which isn't interesting at all. Okay, so another useful thing that you might want to pull out here, especially if you're fitting a model with multiple MCMC chains, is that we might want to preserve our chain order to make sure that we're applying different individual diagnostics like autocorrelation or any of these tests of stationarity to each individual chain. Because each chain is starting from a different starting point, we can assume that each chain is independent. And so previously, when we were calling that extract function, we were using one of the default settings, which is that it takes the posterior draws from each of the three chains and then mashes them together without really preserving any identity with respect to which draw was coming from which chain in which order. So that setting is changed using this permuted argument, and so by default permuted equals true. But if we want to look at each chain individually, we can change permuted equals false, which is kind of what this last line of code shows. And so in this case, we're passing in again our fitted lm underscore intercept object, the parameters that we want to get summaries for, and then we'll get different summaries by chain if we set permuted equal to false. Okay, so now that we've kind of talked about how to manipulate all that stand model objects, we can move on to applying this to the kind of time series models that we're talking about in this class. So for starters, we'll start with kind of the random walk model, and so the random walk model is just illustrated with this equation above, and we'll fit this model to just some basic temperature data in the air quality package. And so in this case, we're going to use our once we've set up the model, we're going to use our same. This is pulling in the temperature. We'll use our same fit stand function here, and again, this is going to take in our response variable, which is temperature. And then there's a couple different arguments to this fit stand function that we want to specify for this random walk model. So before we fit model name and set it equal to regression, in this case we'll set it equal to RW for random walk. And then there's a estimate drift argument, which can be set to true or false. In this case, we will not estimate that drift term, but assume that everything's stationary. So in this case, the model will be saved into this new stand-fit object called RW. Okay, so so we've talked about some visual ways to kind of diagnose whether or not models are converging or not. Another way that I think is useful to identify convergence is to use to look at this R hat diagnostic. And so R hat by default gets spit out in the summary of a stand-fit object. And in an ideal setting, you would want to report that all of your parameters in your model converged and their R hat diagnostic was less than some threshold. And so depending on who you ask in fisheries or ecology, people use slightly different versions of R hat. I think that in most of the work that I've done, I've used values of I want to see values of R hat being less than 1.05, for example. Some people are even more conservative and use values of 1.01. But in an ideal world, you want to see very small values. If you have R hats that are in the neighborhood of 1.2 or 1.3, that's much more problematic and kind of indicative that something's not converging. So we've written this summary function so that we can summarize, or I think the summary function is actually coming from the rstand package. In this case, we're gonna summarize our stand-fit object. We're going to specify what parameters we want to create summaries for. In this case, we'll just do a summary for our observation variance, or sigma. We'll specify the probabilities or the credible intervals that we want to generate at 10% and 90% of the density. And then we'll look at the summary object here using this function. What this object looks like is that we have the mean and the measures of uncertainty, credible intervals. This is the effective number of parameters that were generated. And so remember, we had we had 500. We had a warm up of 500, 500 iterations saved, and then we did that 3 times for 3 MCMC chains. And so having an effective sample size of almost 500 out of that seems pretty okay. The R hat is less than 1.05, which is also a good sign. Normally, this is also problematic that if it's smaller than 1, and so I think that this would again is probably indicative of this just needing to be run for more than the 500 or the warm up of 500 that we had specified initially. Okay, so that was kind of what the random walk model looks like. Kind of moving on, another thing we could fit is kind of this this univariate state space model, and so in this case, we have kind of an autoregressive state space model where we have a phi parameter controlling the degree of autocorrelation between time step t-1 and time step t. Our process deviations are assumed to be independent and normally distributed with some variance or standard deviation parameter q. And then we layer on top of that the data model or the observation model where we have our normally distributed response variable y are centered around our mean, our predicted values. These are the latent states x sub t, and they have some standard deviation representing the observation variance denoted by little r here. And I've denoted this to be little q and little r just to be consistent with kind of the Mars notation of q and r for the process and non-process variance matrices respectively. So one of the interesting things we might want to do here is compare how the model performs with and without this autoregressive parameter, this phi here in that process model. So does the model is there strong support or weak support for including that parameter, or is it essentially a random walk if we don't include it? And so we'll fit this model 2 times. Again, we'll use our fitstan object fitstan function. We'll fit this model to the temperature data. In both cases, we'll assume that we'll turn that drift parameter off. And then we'll fit 2 different new models here. One will be called SSAR for state space autoregressive, and the second will be called SS_RW for state space random walk. And so the random walk model will not have that phi parameter included, or rather phi will be set to 1. In the case of the SS_AR model, we are estimating that as a free parameter that's again constrained to be between 0 and 1. Okay, so these are what the estimates look like. The shaded region just represents the posterior mean along with the credible intervals. And again, the blue dots here are data. These are the estimates from the AR1 state space model, and these are the estimates from the random walk state space model. So flipping back and forth between these, we can see that they're basically identical, which is probably not that surprising. We can look at them even on top of each other, and we can see that the shaded region is essentially identical for both the random walk and the AR model. Both of them fit the data really well. Both of them are also very flexible. You can see they really capture these big swings. Swings in the mean. So why is that? Why might these 2 models be basically telling us the exact same thing? One quick way to look at it, I mean, intuitively, we can think that if the random walk model is assuming that phi is 1 and the AR model estimates phi to be essentially 1, then both models would give us basically the same predictions, and that's exactly what's happening. So we can look at making a density plot here using I talked about the stan_dens function. We can make a density plot of what that phi parameter looks like and see that the posterior these values are all essentially close to 1, which is kind of consistent with that random walk model where we would set phi to 1. So this is somewhat intuitive, but this is just kind of how we would diagnose that those 2 things are giving us the same answer. Okay, so we can also look at, we didn't really talk about this before, but we can also generate kind of derived quantities from the output from these, because all of these predictions are densities and valid probability distributions. For example, we might want to ask, what's the probability of temperature in the model at any point exceeding 90 degrees? And so in this case, we can do a couple things. We can first extract the predictions from from our fitted state space AR model. Then we can calculate how many of those predictions exceed 90 degrees, basically what fraction of those exceed 90 degrees, and then spit it out. So in this case, we would estimate that about 7.8% of the time we'd get estimates of temperature, or the probability of temperature exceeding 90 degrees is about 7.8%. Okay, so moving on to some more complicated models. One of the other things we talked about a couple weeks ago was dynamic factor analysis, or DFA. And remember, DFA is just a kind of a multivariate time series approach for kind of synthesizing multiple time series of data into identifying a few or a reduced number of kind of underlying processes or trends. And so in this case, we'll fit the DFA model to some to the data from the Washington plankton from Lake Washington. It's super confusing. There's 3 different versions of this data in the Mars package, and we'll use the one that's been kind of log transformed. So just as a brief reminder, if you haven't worked with this data before, we've replaced any of the values of zeros. There's only a few of these with NAs, assuming that the species was there. It was just not calculated. The zeros were not actually zeros. They were just represent NAs because the species wasn't observed. The data then were z-scored, and so these all have mean 0, standard deviation 1. And then just for simplicity and model fitting, we'll only use data from 1980 to 1989. And so, and then further, I guess we'll only use 5 groups here, which are kind of listed in this phytoplankton array. And so in this case, we're subsetting the data, as I said, to be between 1980 and 1989 here, subsetting to just be these groups. And then we'll look at what the actual data look like. So this is kind of what the densities, these are the log transformed. These have been log transformed and z-scored. We have stationary trends for probably 4 of the 5, and then the unicellular were kind of decreasing slowly, especially in the latter part of the time series. And they also experienced a couple extreme negative events. So just for starters, we'll we've got 5 time series, and we will fit a 3-trend model. So before all of the univariate time series models that I was talking about with Stan at our ATSAR library, all of those models were fit using the fit-stan function. Here we're also going to introduce you to another function that we've written called fit_DFA. In this case, we'll fit the DFA model. Our inputs here are just going to be the data, and this will be we'll use the transpose to pass in this data frame, specifying the number of trends. And again, we don't have, like with the fit-stan function, we're going to be assuming that we're going to be fitting by default three MCMC chains with a warm-up of 500, a burn-in of number of iterations of 500, but you can change those easily. Okay, given that we've fit our model, we've stored this stanfit object in mod_3. Just like Mars, we have to rotate our trends, and so the exact same process needs to be taken here. And primarily, I think that there's the main justification is for identifiability. One thing you can try is that if you want to use the Mars package to do this, you can, or you can use our fit DFA function. But if you start reordering the time series of for a time series model or for a DFA model with multiple more than one trend, and you start reordering the time series, you're going to get slightly different answers every time you run it. But once you rotate the loadings and rotate the trends, you're going to get the all of those answers will be the same, and they will be not sensitive to the time series order. So I think like with Mars, we learned that Varimax rotation was the way to go, or the default in Mars, and we'll use the same here. And we've actually written a function to do that for you called rotate trends, which should make things fairly simple. So once we've rotated those trends, we get a few different things out. We get these are just the different properties of the object. We get z underscore rot, which is the rotated z matrix for every individual MCMC draw. So if you do this, if you have 1,500 draws or 1,500 samples of the posterior, you're going to get 1,500 z matrices. Same thing with the trends object. We have the means of the respective values of z rot and the trends with z rot underscore mean and trends underscore mean. And then finally we have the quantiles, the 95% quantiles for the trends with the trends underscore lower and trends underscore upper. So those are just useful summaries for doing some quick calculations of those estimates. Okay, so by default, with our fit DFA function, the basic structure of this is diagonal and equal. We can extend this to be diagonal and unequal or have shared variances. And you can do this using this var index argument fairly easily. We've also got some more, just like with Mars, we can specify more complicated variance structures. So I think it should be pretty straightforward if you're interested in applying Bayesian DFA to your class project. Again, come chat with me, and I think I can make sure that you have the code that you need to actually do the analysis. Okay, so one of the other things that I think is probably useful, and so I think is thinking about kind of some of the uncertainty intervals on our latent trends or our latent states. And so, often when we're doing DFA, we might show just what the trends look like. I think it's also probably very useful to show our uncertainty about those trends, which I think is a good way to present kind of our confidence or our understanding of how precise those are. So one way to do this is just to take the harbor seal data from Washington, and we'll look at the effect of missing data on what that does to the uncertainty in the DFA trends. So the model that we wanted to fit here was just, this is again, we have 5 different kind of substocks. For the I guess this is the inland stock, so there's 5 different populations within that stock. They have different log transformed abundances. For the most part, they're increasing over the last 20-25 years. And so to fit the model, we're going to use our fit DFA function here, and just for simplicity, we'll fit a one trend model, which is kind of the basic. We'll extract the fitted model, the fitted parameters and fitted states using the extract function in the rstan library, and then we'll just make a data frame which contains the predictions from or the mean predictions of that trend, as well as the lower and the upper 95% credible interval for that trend, and then we'll just use just display with a kind of a geom ribbon plot, just kind of show the uncertainty around the predictions for that latent trend. Okay, so that was kind of the full data set. And if we wanted to drop out data, one way to look at doing a sensitivity would be to, for example, drop out every other observation, or drop out observations in some other kind of random sampling fashion. And you could look at how these uncertainty estimates for the trend would balloon as you dropped out those observations. One of the interesting things here is that, back in 2 slides ago when I showed kind of what the raw data looked like, we had samples or observations for 3 of the populations for most of the time series, and I think the Hood Canal and maybe the San Juan stock have only been observed more recently. So we have more data in the latter half of the time series compared to the earlier first half, and you can see that reflected here in our uncertainty estimate with respect to the trend. And that if we look especially between years, say 1 and 5 or 1 and 7, we have higher uncertainty, kind of the uncertainty balloons, because we have less data, less information. And so I think that if you're going to do DFA, presenting both the mean estimate of the trend as well as some measure of uncertainty around that trend is probably useful. Okay, so last week Mark had also talked about fitting dynamic linear models, which again are, the dynamic linear model is essentially a regression model with a time-varying intercept or time-varying coefficient. And so in this case, we will kind of replicate what Mark did with his logit transformed estimate of Columbia River salmon survival. And so I think there's kind of 2 ways to set up this DLM. One would be to set it up so that we had the random walk in the intercept. Another would be to have it set up in the slope. So for this example, we'll just start with having it set up in the intercept. We'll go back to using our fit stand function as we did before with some of the univariate state space models that I was demonstrating with Stan. In this case, we'll set the model name to be DLM_DLM-intercept, and so this will fit a DLM with a random walk in the intercept. This is kind of what this is just kind of an ugly way to get our extracted estimate of the trend, or estimate. I'm sorry, it's a ugly way to get our time varying estimate of the intercept out of the fitted model object, and then we can show what that looks like. This is the random walk and the estimated intercept through time, again using a kind of the geom ribbon plot, showing our uncertainty around that. And again, this is the 95% credible interval around that trend. You could change that by changing these quantiles up above, and you could get quartile or any other different interval you wanted. Okay, so then we'll take it a step forward, and in addition, we had just fit the model with the time-varying intercept. Now we'll fit a time-varying slope model. In this case, we'll pass in, we have our response data, the salmon survival, which has been logit transformed. We'll pass in the April, this is April, I think Columbia, maybe it's upwelling, index as a covariate, and then our model name, it's going to have to change now to be DLM-slope. We can see here that the model just has some convergence problems because the betas are estimated to be, they're for the most part they're pretty small for most of the time series, but we have these blips here where things really blow up, and when they blow up, not just does the mean get pretty far off, but the variance does too. So I think that these are just indicating that the model is having a real hard time converging. Taking this one more step further, we can fit the model with both the time-varying intercept and the time-varying slope. And so in this case, we want to basically create a matrix, or a model matrix object that would include both an intercept and the slope. And so that's one kind of shortcut that I use to do that is using the model.matrix function, where you can specify a linear regression model object using LM very simply, and then extract the model.matrix, extract the design matrix from that fitted regression model, which is just kind of a dummy model. But we can pull out the design matrix using model.matrix and pass that in as a covariate to our fit stand function, where we're changing the model name to DLM here. And so in this case, we're going to be you can do that yourself, but basically that's one way to fit both the time varying intercept and time varying slope at the same time. Okay, so I'm out of time, but I just wanted to recap and say that Stan has been a really useful tool since its inception, and it's a very flexible and powerful language for basically doing everything that Mars can do and a lot more. It's very easy to learn because the developer community and the number of applications is just growing so quickly. It's widely used by students in SAFs and UW and Quirm, and so there's a huge community of people to answer questions and help you with code. And it's super flexible in that it lets a lot of parameters be shared, or hierarchical models can be developed pretty quickly. And again, going back to the idea that a lot of our data are just not normal, and so having tools that let us model lots of zeros and data that are skewed or have long tails in weird ways is really useful. And so if you wanted to use Stan, I think that we're all willing to help. And please come to us with any questions or modeling issues that you run into. All right, thanks.